Here's our objective. Utilize, I mean use, and K is the rate constant for late law, rate law, and the half-life is how long it takes half of a radioactive sample to decay. All right. Now, I wanted to review what decay looks like, and here I got 100 atoms, and if they decay, 50 of them are going to decay. All right. And if I have 50, how many are going to take? 25 are going to decay. If we have 25, 12, or 13, you can't have a half atom decay. All right. So that puts us right about here. Now we've got 6, and then 3 or 2, and then 1, and then you'd have none. All right. And I just wanted to give you a visual of what it would look like. And now for rate law, we're talking about this. We're talking about this K. And this thing comes from people studying numbers, studying actual data. That's how you know what it's going to be. It is a constant. It's a number. Therefore, it's a number. Ks are positive because your rates are going to be positive and you can't have negative concentrations. They depend upon what you got. It's going to change from one reaction to the other. Baking soda and vinegar has 1K, as does acid and bases reactions. And they will, for chemical reactions, they're going to, if you make it hotter, that could influence the K. If you make it colder, it's going to influence the K. For decay, for actual decay, the Ks are a specific value. And I've said it's like speed in the sense that it's always going to be positive. All right. That word there is positive. All right. Now, also, I want to talk about these graphs because the graphs of first, zero, and second order, because the graphs are going to help us see where the equation comes from. Now, this is first order, or sorry, zero order. What am I thinking? And your K value is the negative of the slope. All right. This is first order, and your natural log concentration of X, where and the K value is the negative of the slope, the K being the rate constant. And second order, when I take the reciprocal and I graph it, I get this relationship, and my K is the slope, the value of the slope. All right. And if I had data, how would I figure out what was what? Well, I would graph these three things, or I'd look at the numbers and see where it was going up in a linear fashion. And I'd look for, as it says, a linear relationship. And here you can see that's definitely linear. Now, excuse me, half-lives, or excuse me, no, decay or radioactive decay is always first order, always, always, always. All right. And it's going to look like this. And what we're going to look into now is when I look at the actual data and I look at the graphs, an equation is generated. It's incredibly fascinating. I just wonder who was the person that saw it. So if you look at some, oh shoot, uh, if you look at some data, I made some data, and then I'm going to show you some not made up data where I gave an isotope a half-life of 10 years. And you look at the graphs, you clearly can see that this is the linear one. So that's definitely, that decay is definitely first order. Then I did it with uranium. Uranium has got 4.9 billion years. All right. Once again, you can clearly see this linear relationship. Then I did it with carbon. All right. And the reason I did it is because when you look at these values, you can see a pattern emerge. And from the pattern comes the equation. So the slope of the first line was this. This gives me my K value. It really shouldn't be per second inverse because all of my times were in years. So it would be inverse years in this regard. All right. Here's my half-life. It's 10. Here's the second one. And here's the third one. Now, I don't see a pattern yet. Do you? I mean, these just look like a bunch of random numbers to me. So I don't see the pattern. And I'm going to try to make the pattern a little clearer. If I make the half-life 100, this 0.0693 comes up again. Here it's just e to the negative third. All right. Here's my isotope 2. I did it. And there it is. All right. So there it is. That's really interesting. Now, here's where it gets really cool. If I take these two numbers and I multiply them, I get this number, 0.693. And then if I do the same thing down here, I get the same number. Well, what happens if I do that with these two? The same number comes up. I get the 0.693. So from this, and from, excuse me, from this, now I can come up with an equation where your half-life is going to be this number, 0.693 divided by k, or k is 0.963 divided by the half-life. All right. Now let's say how we can use this is we can predict rate constants from a half-life or vice versa. If I knew the rate constants of something, I can figure out if it's decay, I can figure out its half-life. So I want to know the rate constants of potassium 40, and potassium 40 is it's what's in bananas. It's a really long half-life. It's like basically forever. 1.29 billion years. So following the four-step format, all right, the first thing I know my half-life is this, and I want to know my K. So I'm going to plug it into my formula, and essentially these things are going to swap, where I'm going to have K equals 0.693 over my half-life, all right? That's my formula. And then here's what I would get, all right? And then here's my K. And then I would write this in scientific notation, and it's 5.41 e to the negative 10th years Ks. So that's my rate constant for the decay of potassium 40. All right. I hope this has been helpful, and you guys have a good day. Bye.